A computer, in its strictly isolated state, is an electronic machine designed to process raw data into meaningful information. However, an isolated machine is limited by its own local hardware. Without a connection to external entities, its processing power and data remain inaccessible to other systems. When we grant a machine the capability to connect to a much broader framework, we define it as a node. A single computer node attempting to process a massive task alone is limited by its local specifications, creating a hard bottleneck. Networking is the explicit process of connecting independent nodes together. This connection bridges the gap to share data, hardware, and services. These systems are engineered along two distinct axes: physical geographic scale on the horizontal axis and logical control topology on the vertical. Modern network engineering requires a constant balance between these two axes. As the physical reach of a network expands, the logical rules governing its nodes must also evolve to maintain stability. This is a personal area network, or PAN. It is the most localized network scale, typically serving a single user within a range of a few meters. This image shows a common implementation, the direct Bluetooth connection between a smartphone and headphones. On a logical level, a PAN operates on a peer-to-peer control topology. In this decentralized setup, devices communicate and share resources directly with one another, without the need for a central server to mediate the interaction. The P2P model is highly effective for small setups because it eliminates the need for dedicated server hardware, keeping both implementation time and equipment costs low. While effective for a single user, the lack of central authority in a P2P network makes it difficult to secure as the organization grows. A local area network connects devices within a limited area. This diagram illustrates the peer-to-peer model, where workstations share files directly. The red text notes that every machine maintains its own local user database, meaning passwords must be managed individually. This creates an administrative bottleneck. Updating security protocols across dozens of independent workgroup nodes results in a disorganized cluster of access errors and inconsistencies. Geographically scaling a network eventually forces a transition in control topologies. An enterprise infrastructure cannot be effectively maintained through manual, decentralized management. The structural solution is the client-server topology. As seen here, this is a centralized model where clients, such as workstations and smartphones, point their requests toward a dedicated central server that provides the required services. Centralization solves the workgroup bottleneck by establishing a single point of control. Administrators can manage security policies and user data from one authoritative location. In large-scale Windows environments, this is implemented as a domain. In a domain, user accounts and system policies are dictated universally by a central domain controller. In a domain environment, a user can log into any connected PC using a single centralized account, overriding the restrictions of local hardware. This enterprise-grade scalability comes with specific trade-offs: the introduction of a single point of failure and higher hardware costs due to the need for dedicated servers. Logical topologies rely on a specialized physical layer of hardware to actually route and distribute data packets between nodes. The hardware baseline is the network interface card, or NIC. This physical component is built into a device to allow it to connect to a transmission medium, such as a cable. This SOHO diagram shows the central switch acting as an internal distribution hub, linking local devices like PCs. Connected above it is the router, the boundary device responsible for forwarding data packets and serving as the gateway to the internet. The physical manifestation of a domain requires the precise sequence of NICs, cabling, switches, and routers to ensure the logical rules are enforced across the hardware. Beyond the single office is the Metropolitan Area Network, or MAN. This diagram illustrates how a MAN connects multiple localized LANs across a specific city or metropolitan region, creating a broader regional architecture. The ultimate scale is the Wide Area Network, or WAN. This map of undersea fiber optic cable routes shows how WANs connect networks across entire continents, facilitating global communication. To bridge these vast geographical distances, the network shifts away from localized Ethernet cables in favor of high-capacity technologies like fiber optics and satellite links. From a simple Bluetooth connection to a global domain routed via undersea cables, the core objective remains constant: engineering the physical pathways and logical rules necessary to connect independent nodes.